Today we'll be talking about clustering and dimensionality reduction and more generally about unsupervised learning. So just a quick recap of sort of the way we can think about breaking down topics in this class. We've spent basically all the class thus far on supervised learning and things related to supervised learning. Of course, a lot of these concepts can be applied to both supervised and unsupervised learning. But we've looked at all of these concepts, with the exception of probabilistic modeling, in the context of supervised learning. Starting this lecture, for the next 3 to 4 lectures, we'll be looking at unsupervised learning. And then in the last part of the course, we'll be looking at probabilistic modeling as it relates to both supervised and unsupervised learning. And so yeah, today we'll be looking at unsupervised learning, looking at loss functions, models, learning algorithms, so on and so forth. So today we'll look at 2 forms of unsupervised learning. The first one is clustering, and the second one is a form of dimensionality reduction based on latent factor models, which is also closely related to concepts like matrix factorization. If you've taken 156, the second topic may be pretty familiar to you already. Okay, so what is clustering? Sort of intuitively, clustering is exactly what it sounds like. Clustering is the process of grouping data into clusters, right? A cluster is simply a collection of points. And intuitively, you would want the data points inside the cluster to have very high similarity, at least relative to the data points between clusters, which you would want to have, relatively speaking, much lower similarity under some definition of similarity. So let's go through a very simple example. So suppose this is our data set, and here in the unsupervised setting, recall that we have no labels. We only have the input feature vectors. And so we have here a data set, unlabeled, we have no labels, in a 2-dimensional representation. How many people think there's 2 clusters here? 3? All right, I won't insult your intelligence by asking 4. So yeah, there are 3 clusters, and so let's posit that there are 3 clusters. And how might we find them, right? And so here's one very simple algorithm. The first thing we're going to do is have a random initialization of the cluster assignments. And so I'm jumping ahead of myself. I should have had coffee. Sorry about that. So here are the cluster assignments that we'd like to discover, right? I'll get to the algorithm in a few slides. I'm way ahead of myself. So unsupervised learning, just to talk about it a little bit more formally, is we're given an unlabeled data set. So here our data set S, right? Before it used to be a pair XY pair. Now it's just a single X, right? So there's no labels, only input features. And the goal is to find some sort of hidden structure, right? In the data, right? Because we're not trying to predict some target label. This is somehow the only thing that we can do, right? And the hidden structure in the case that we've been talking about first is a clustering of the data. We'll look at other ways of finding hidden structure in the data as well, such as building a probabilistic model over the data, dimensionality reduction, just some sort of low-dimensional summarization of the data that you can use to explain some salient features of the data, or features is a loaded word, some salient characteristics of the data, right? And so to think about clustering, right? Why might clustering be useful? Well, if we believe that these clusterings summarize the high-level salient characteristics of the data, then we can simply, for example, inspect the cluster centers to get a sense of what kind of data this data set contains, or only inspect a few representative data points per cluster, right? This gives us a handle to get some insight about what are the salient characteristics of this data set without having to inspect every data point manually, right? And so here's just a simple example from a paper from a while ago, where it's a very simple example. They went on image search, and they searched for images related to the word Pluto, and then they ran a clustering algorithm. And so each row here are some representative images of a cluster, right? And so I'm not too familiar with everything here. I guess there is some sort of furniture brand named Pluto. There's things related to planets, the dog, and so on and so forth, right? The cartoon dog. And so just from looking at this, we can get a sense of what are the different types of images out there on the internet which are relevant to the word Pluto. Right. So another thing that is interesting about clustering and other forms of unsupervised learning is that this allows us to have a compact pre-processing of the data before supervised training, or some sort of downstream processing, right? And I'll get into this in a little more detail later on. Okay, so now let's talk about a clustering algorithm. This is k-means. It's a centroid-based clustering algorithm. And so the first thing we'll do is we'll have a random initialization of the data points into the 3 cluster memberships. So here, the cluster memberships are color-coded, red, black, and purple, and the assignments are completely at random, right? And so now what we're going to do is we're going to compute cluster centers. And here, cluster centers are simply the sort of the center of mass of each of the clusters, right? And so you can solve for that by taking the average of the locations of all the data points assigned to a specific cluster. And so here you get the cluster centers of the purple, black, and red. And if you are a super nitpicky student, I did not draw this using a computer algorithm. I drew this by hand, so it might be a little bit off. But it's the qualitative thing I want you to get from this slide. I'm just going to say that right now, because the last 3 years, someone always nitpicked. Okay, here we go. And so now here's how the algorithm works. We have these clusters. We have these cluster centers, right? And now we're going to simply assign every data point to the cluster center that it is closest to. And so that now it looks like this, right? And now we're going to recompute the cluster centers based on these new cluster membership assignments, right? And it looks like this. So if this is what it was before, now it's what this is what it looks like now. And then we're going to reassign data points to clusters based off which cluster center it's closest to, right? And now it looks like this. This is what it was before. So a few data points have changed. Now we're going to recompute the cluster centers by averaging taking the average location of the data points for each cluster. And now we compute the new cluster centers. We recompute the assignments, recompute the clusters centers, recompute the assignments, recompute the cluster centers, recompute the assignments, recompute the cluster centers, so on and so forth, until eventually we'll reach a fixed point where nothing changes, right? This is typically some sort of local optimum. In this case, it's a global optimum of the objective function I'll describe in the next slide. And now we're done, right? This is the solution that this particular algorithm will return. And in this particular very simple case, it returns the answer that we were looking for. Any questions? Yes?
So I've seen variants where you initialize the centers randomly rather than the points. Is there an advantage to doing one or the other?
I am unaware of any sophisticated thinking about the advantages of one or the other. Yes?
How do you know to pick 3 if you don't know what it looks like?
It's a great question. So how does one determine how many clusters there are? There's a few different ways of going about doing it. The most popular way that people do it is through some sort of validation, right? So we talked about validation typically in terms of measuring some sort of error or on some holdout set, some validation set. We can do that here as well. It's a little bit more complicated because it's unsupervised, right? And so what people typically do is they actually plot an entire curve. And I probably should have had a slide on this. And the curve is on the x-axis is the number of clusters, and on the y-axis is the residual error of fitting the data. And this might make more sense in a few slides after I talk about the formal objective. But typically it's done through some sort of validation. People have proposed more sort of meta approaches where it tries to infer the number of clusters automatically. Those have variable success rates on the problem. So if you still have that question, why don't you ask it again after we go through the next few slides. It should be more obvious. So any other questions? Yes?
So you mentioned a validation set. So how do you validate without any labels of the data?
Well, validation set simply means measuring something about the model's predictions on a holdout set. So we would simply take a subset of this data, hold it out, train a model, and here the model is simply the cluster centers, right? And then see how well these cluster centers under some metric explain the held out data. And this will become a little bit more apparent once we look at the learning objective of this algorithm that I described, the k-means algorithm. And so this is the learning objective. Basically, we're going to partition the data set S into k non-overlapping clusters. These are it's a partitioning. Each partition corresponds to a cluster. We're going to infer, we're also going to learn the cluster centers. You can think of these as the parameters of the model, right? And the loss function we want to minimize is the square distance between every data point in a cluster with its cluster center. So this is the learning objective. If you do a little bit of math, this is equivalent to the unnormalized variance of each cluster. The variance of the cluster is simply the variance of how far the data, how much of a spread there is within in that cluster of the data within that cluster from the center. So this is the learning objective, right? And so the lower we can get this number, right, the better the clusters, this clustering model, these cluster centers, explain the data under this metric, right? The residual unexplained variance or variability in the data is reduced if this quantity is reduced. Okay. So the algorithm that we saw pictorially in the last few slides is called the EM algorithm for k-means. And so here's how this algorithm works. There's sort of two steps. It's an alternating optimization procedure. There's an E step. So EM stands for expectation maximization. There's an E step and an M step. And in the E step, we estimate the cluster memberships, right? So if you think of, you hold the cluster centers fixed and you estimate the cluster memberships. So that's one of the steps that we looked at pictorially. And in the end step, we estimate the model parameters given fixed cluster memberships. And so essentially what we're doing is we hold one of these sets of variables fixed and optimize the other one and vice versa. That's what EM is doing. Right. So in the E step, we hold the cluster centers fixed and we re-estimate the clusterings, so the cluster memberships. Right, and so we simply we solve this objective function while holding the cluster centers fixed, and it's straightforward to see that for every individual data point x, this quantity is minimized by assigning it to the cluster of which its cluster center it is closest to. That was a very convoluted sentence. We assign each individual x to the cluster with the cluster center that it is closest to. So this is a very straightforward step. The M step, right, says we're going to hold the cluster memberships fixed, and we're going to estimate the cluster centers, right, the new cluster centers. And so if you look at this objective function, we can estimate each cluster center independently, right? That's one term in this outer summation. And because our penalty is squared error, it's simply the mean of all the data points in that cluster. That's it. And that is the entire k-means algorithm. It's one of the most popular clustering algorithms. It's probably the most popular clustering method used in practice today. Any questions on the procedure? Yes.
Given some set x, if you hold what each of those data points are, the optimization over where CK should be is convex, right?
Each individual step can be optimized exactly.
Okay.
The joint optimization is non-convex.
Okay.
Yeah. So you can get stuck in local minimum. Okay, so what have we done here, right? We've basically, there's a few ways you can interpret, actually I should, before I go on, let me readdress the question that was asked about how do you choose a number of clusters. So there's a few different ways that one can do it, and I should have had a slide on this, I apologize. So one way that people often do is they draw a plot where the x-axis is the number of clusters, and the y-axis is the objective function, either on the original training set or on a validation set, right? So if you hold the cluster centers fixed, you could compute the cluster memberships of all the data points, either on the training set or the validation set, and then you measure this squared error, right? And typically, the squared error will drop as the number of clusters increases. In particular, if the number of clusters is equivalent to the number of data points, then this reconstruction error is 0, right? And so what people typically do is they plot the squared error as a function, so that's the y-axis, as a function of the number of clusters, and you get sort of a decrease in the squared error as the number of clusters increases. And in many data sets, if there is a natural clustering of the data, the error will stop dropping so rapidly. It will start dropping it will sort of flatten out in terms of how quickly it drops. And so, because this is sort of something that's often used as in some sort of downstream application, people just sort of use this type of validation curves to sort of eyeball how many clusters are appropriate. If there's some sort of hierarchical structure in the clustering, for example, if there are subcluster structure in the larger clusters, you might get multiple bends in the loss curve as it drops in terms of the function of number of clusters. Yes?
Like typically, what is K relative to like the number of data points we have? Is there a guideline?
There's no hard and fast rule.
Is there like some point at which it's not fast enough to run?
Oh, speed. This is pretty fast.
But
I mean, if you're dealing with 1 billion data points, then people have done various approximations to k-means. There are methods called core sets and other methods where you can sort of, for example, this is beyond the scope of the course, but there's a method called core sets and other similar methods where you can sort of process the data once and realize that this data point is almost always going to be clustered in the same cluster as these data points, right? This is something that you can detect sometimes. In which case you can throw out most of this data, represent this entire region with a single data point, right? And you get a clustering, and then you always get a clustering that is going to be almost the same as if you had all the data points. If there's a lot of redundancy in your data, this is something that can work very well. You can speed up the clustering method by orders of magnitude. Those type of things really only matter if you're in the millions or billions of data points. This is a pretty fast algorithm, and if you think about it, it's embarrassingly parallel, right? Like assigning a data point to a cluster membership, if you have 10 cores, it's 10 times faster by default. Yes?
So in terms of the number of clusters to choose, can you add a kind of regularization?
You can. So you can impose, so the question was, can we add a regularization term in terms of choosing the number of clusters? And you can. So people who work on probabilistic clustering, where they have some prior assumption about how many clusters are possible, like a distribution over clustering. So you can take a more probabilistic interpretation, in which case, you think that lots of clusters are unlikely, right? And so people have done that. How well that works, it has mixed success. Sometimes it works really well, sometimes it doesn't. Like if your prior assumption, if your regularizer is just really wrong. Okay, so what's happening here is that one way to interpret what's happening here is that we are summarizing the data by cluster membership, right? Every data point, which could live in a 1,000-dimensional space, here it's 2, but in general it's high dimensional, now lives in the 3-dimensional space in this example, right? Where it's the 3 dimensions is the cluster membership, right? So we've reduced a high-dimensional data point down to its cluster membership. And depending on how you interpret things, one interpretation is that, well, the variability within a cluster is just some noise in the data that we don't want to model. We don't care about modeling because it's some lower order effect that we don't care about. The cluster membership captures the high-level characteristics of this data. And in some sense, under the clustering model, this gives you the best quote-unquote reconstruction of the data, right? If we were to reconstruct the data set, it would sort of say, well, I have 3 clusters here, here, and here. and then the reconstruction error is the distance from each point to the cluster center. And under that type of reconstructing of the data, this is somehow the best that you can do. Okay, so just to recap k-means, it's a centroid-based clustering method, and because it defines clusters using a notion of centrality, here minimizing the variance of the clusters. We saw we're using the expectation maximization algorithm. There are also probabilistic variants called Gaussian mixture models. We'll again talk about probabilistic models in the last part of this course. And k-means and similar clustering methods are useful when the centrality assumption is good. But they can fail or not work so well when the centrality assumption is bad, right? And so here's a thought experiment. I'm giving you some data sets, and I'm giving you two clusterings, right? One in the black and one in the orange, right? It's actually unclear which one is the preferred cluster. It may even depend on the application that you're going to use it for. And that's because the notion of centrality here is much weaker than in the data set that I showed you in the previous example, yes?
Are there models that model that kind of hierarchical clustering that you mentioned before? Like you find a few centers for the major clusters and then the
So people have proposed hierarchical k-means. You can look it up. People have proposed many versions of hierarchical k-means, and where they do something like this hierarchical notion of centrality. I'm going to present a completely different algorithm here. It's a very fundamental algorithm, and you can mix and match them. People have done that. Yeah. Okay, so the other form of clustering, the other major form of clustering approaches is called linkage-based clustering, right? So k-means uses a centroid clustering structure, so cluster data points are close to the cluster center, but sometimes a linkage structure is better. And so I'm going to describe a particular method called agglomerative clustering. And here I'm going to just describe it by picture. Okay? It's a very simple algorithm. So the first thing we're going to do is we're going to connect the two closest data points together. Like that. Okay? And then we're going to repeat this process. And again, this might not be the actual closest data points. Not drawn to an exact scale. And so this is how the process works, right? And here's something interesting happens, right? So here I'm going to connect this data point to this data point, because these two are the next two closest data points, right? And what this defines is this actually defines a clustering of these three data points, because these two data points are already linked. Right? And this process continues. So now we have a clustering of these three data points, because these two data points are already linked before you linked this guy to this guy. And this process continues recursively until the entire data set is linked. There we go. All right. So can anyone tell me what algorithm that was? Yes?
Minimum spanning tree?
Correct. That was Kruskal's algorithm for finding a minimum spanning tree, also known as agglomerative clustering. Or maybe that phrase should be vice versa, right? So what I just described is equivalent to finding the minimum spanning tree, right? One thing that's sort of interesting is that the order in which the edges are added, you can use that to define a hierarchy of the clusterings, right? So the order in which the edges were added, depending on, you can use that to sort of define a hierarchy, and then you could say which level of the hierarchy you find more useful for whatever application you're using. Yeah.
When you connect, once some set of points is completely connected, you can't make any other connections between those points. It wouldn't choose to make. So say like the first 3 points that you classified over here, the next it wouldn't make a connection connecting the two that are disconnected once you make the other two connections, right?
I do not understand.
So we have this in the upper right corner, we found
Uh-huh.
the 3 data points that are connected. You wouldn't complete that triangle, wouldn't it?
No. We're finding the minimum spanning tree. Yeah. They are considered connected. Yeah. Or we're connecting disconnected components, and the distance is measured by the shortest distance between any two vertices within those two disconnected components. Yes.
So big data sets, computing this set of all edges would be, it's quadratic, right? In the sense of a data set. So are there ways to make this scale?
Again, for larger data sets, people probably do some sort of approximation, right? You could just decide that data points that are this close together must belong to a cluster, right? So maybe each of these is actually a collection of 100 data points, and we just decided that they're just a supernode, right? So I mean, there are different things that people do. I mean, none of them, all of them depend on certain assumptions that you need to make that you need to be okay with, but that's one. Right? Okay, so that was clustering. It's a very intuitive idea. We looked at 2 different ways of thinking about clustering, one based on centroid notions of centrality and centroids, and one based on linkages, right? And whichever one works well for your application really, it depends on the assumptions you're making and what you want to get out of the clustering. But both can be very useful. I would say that k-means is probably the most popular clustering method, and if people want to cluster their data set, I would typically recommend k-means as the first thing to try, although it is definitely not always the best. Any questions on this? Yes.
So if you were try to do the Pluto image classification, how would you transform that into a sort of vector representation?
Right. So how do you transform the images into some representation that you can do k-means on, right? So people typically use image features. Historically, they've used things like sift features and histogram of gradient features. These days, you probably use a pre-trained convolutional neural net, and then you use one of the hidden layers as a vector representation to do k-means on. That's typical people do these days. And we'll actually see something that's a sort of example of this in about a week and a half when I talk about some recent research in this type of flavor. Yeah. Yes.
What's the optimization objective?
The optimization objective, it is literally to find the minimum spanning tree. Yeah. Okay, so that was clustering. It's one way to do unsupervised learning where we're trying to learn some sort of very compact summarization of the data that captures some kind of salient characteristic of the data. In k-means, that salient characteristic was where are the cluster centers, and the quality of that summarization depends on the squared reconstruction error. How far are the individual data points away from the cluster centers of the clusters that each data point was assigned to? Right. Okay. Well, that concept has some limitations, right? Can anyone give me a clustering of this data set? Clearly, there's some interesting structure here, right? But it's actually quite difficult to define a clustering over this data set, right? And so now we're going to look at principal component analysis, which is very, very closely related to the singular value decomposition. In fact, for all intents and purposes in machine learning, the two are basically the same thing. And so in some sense, right, there are sort of 2 principal dimensions of variability, right? So, the data seems to be varying along this dimension and this dimension, rather than the raw native dimensions that the data lives in, right? And so the goal of principal component analysis is to find these directions of variability, right? And recover that from the data set. So we're not looking at clustering, we're looking at finding directions of that summarize a lot of the variability. Right? So, imagine that this data set lived in some high dimensional space, but most of the variability was along 2 dimensions, right? And these 2 dimensions are not sort of axis aligned, they're sort of in some direction that we need to discover in the data. And so that's what this type of unsupervised learning is meant to do. Is summarize the data using a small number of attributes, and rather than those number of attributes being the cluster membership, we want them to be a small set of orthogonal projections of the data. And this will define a new feature representation. And you could think of the orthogonal projections as sort of basically a rotation and then a projection of the data. Right? And that's what this is. Okay. So, all right. So, if this, again, imagine that this data actually lives in a really high dimensional space, and this is just the 2 dimensions of variability. We can then define this new feature representation, right? So I simply just did a rotation of the data, where now I have 2 new feature representations that's different from the original raw feature representation, and now every data point can be defined as this new coordinate system, and this new coordinate system somehow is more meaningful. Right? So a little bit of notation. So hopefully you've all seen most of this before. A lot of these concepts are also covered in the linear algebra recitation earlier in the course. Right? So a matrix U is considered orthogonal if UU transpose or U transpose U will give you the identity matrix, right? And so for any column little u of big U, it is unit norm, so its inner product with itself, its dot product is 1. Any 2 distinct columns, U and U prime, their dot product or inner product is 0, which means the 2 U's are orthogonal to each other, the 2 little u's, right? You could think of a big U as a rotation matrix, right? And U transpose is the reverse rotation or the inverse rotation. So if we have this x, right, and we apply this U transpose x to get an x prime in this new coordinate system, right? This is x prime, where the new 2 coordinates are where the data point lives in this new coordinate system. Then we can reverse this rotation by simply apply the transpose of whatever of U transpose, which is just U, onto x prime, we get x prime. So that gives us the reverse rotation. Right? And the goal of PCA, principal component analysis, is to find a specific U that satisfies some reconstruction loss function. Any questions before I move on? Okay, some properties of orthogonal matrices. So the first one I just described. It's also norm preserving, right? So if I take 2 transform data points, x prime, if I take a transform data point, x prime, and we compute its inner dot product with itself, recall that x prime here is simply U transpose x, right? And so this is simply U transpose x, U transpose x. You manipulate this using standard linear algebra operations. You get something like this. This is the identity matrix, so you get this, right? So this U makes, this rotation matrix is norm preserving, and so therefore it preserves the total variance in the data set, right? Assuming this data set has been shifted so that its center is 0. Right. Okay. So suppose we wanted to find the best summarization of this data set using only one feature, right? So we're going to do a very simple form of dimensionality reduction from 2 dimensions to 1, right? It would be this feature, right? We simply record or encode where each data point lies along this axis, right? Along this axis. And this is an axis that we discovered in the data, right? It's not part of the original raw representation of the data. It's a new feature dimension. It's a new axis, and by simply encoding where each data point projects, right, or lies along this axis, we get a one-dimensional representation of the data, right? We can now summarize the data using a single number, right? And in some ways, this is the best that you can do if you want to summarize this data using a single number, because this axis captures the direction of maximum variability of the data, right? The orthogonal, the remainder, the residual, is the variability of the residual is minimized, right? So, and that'll become a little bit more formal in a slide or two. And so this is what happens, right? So imagine that this axis is little u sub 1, right? So it's just a column of a single column of the matrix. And so the projection, transforms each of these data points to something that lies on this line, this axis. So this is our x prime, right? And then we can reverse that. We can reverse this projection. We can reconstruct the data by simply multiplying this data point x prime by u1, and you get something that looks like this. And this works, of course, for more than just a single dimension, right? If you have a 100-dimensional data set, projected down to 3 dimensions, we can take 3 columns of u, right? Of some u that we found, and then we multiply the original x by this u matrix with 3 columns, and we get a 3-dimensional coordinate system back. Here, for simplicity, it's just a 1-dimensional coordinate system back. And then this would be the reconstruction, right? So for the price we pay for summarizing this data using only 1 dimension is that we lose the ability to reconstruct along the orthogonal direction to this axis, right? If it had turned out that the data, there was no variability along this dimension, right? All the data actually did fall on this axis, then this reconstruction would be perfect. And the imperfection of this reconstruction, you can measure that using the square distance between the original point and its projection onto this line. Right. And so here's the formal definition. So let's see. We have a matrix of all the data points, right? We're going to mean center it. So let's just so that the data set is so the data set is shifted so that the average feature value is 0 for every feature. And then PCA simply says, well, we're going to find a decomposition of XX transpose into this matrix, and the U again is what we care about. And so, this U is assumed to be an orthogonal matrix. Each column is also known as an eigenvector. I'm assuming this is review for most of you. And then this lambda matrix is actually a diagonal matrix, so the off diagonals are 0, and each individual lambda is called an eigenvalue. In this particular case, because XX transpose is symmetric positive semi-definite, all the eigenvalues are non-negative. And we assume that the eigenvalues are sorted in decreasing order. And what eigenvalue and eigenvector means simply is that for any u, any column of this U matrix, if we multiply this original matrix, the data matrix, where we look at the covariance of the features, we multiply it by that matrix, we get the same vector back in the same direction, scaled by its corresponding data. That's simply the definition. How many of you have seen this before? Okay, so about 2/3 or 3/4 of the class. Okay. So right. So we typically you would refer to this feature covariance matrix as sigma. That's often used in the terminology. And so each entry of this sigma matrix, like dd prime indexing over 2 feature dimensions, is the covariance of features in the training data. So if you look at all the training data, how much do these two features covary, right? These two feature values. Right? And we're going to learn, the way we learn, and I'll give you the learning algorithm in a second, PCA, is such that the first column of this U matrix is the single direction of greatest variation, right? So this would be U1 in this very simple example, and this would be U2, right? And so if we project all the data onto U1 and we measure its squared value, it sums up to the first eigenvalue. These are just properties of principal component analysis. So the first eigenvalue says this is how much of the variance of the data that projecting onto the first dimension explains. Right. So therefore, if we were to project this data onto the first eigenvector, and then we reconstruct the data back in the original space by reversing the projection, then the difference between the square difference between these points and the original points is, you can think of it as the residual, right, of the reconstruction, right? And so if we wanted to find the single direction of maximum that captures the maximum variability, it's simply the U such that this loss function is minimized, right? This is the reconstruction loss. And in this particular case, I'm just looking at for a single dimension. In general, you could do more than one dimension. And one can prove that the first eigenvector of the principal component analysis is exactly the vector, the unit vector that minimizes this objective. So I'll just step through this. I mean, you can review this on your own. This is just some ways of manipulating the linear algebra, right? So if this is how we define U, right? U is we define U as the vector that captures the most variability of the data points along its projection, right? So that's what this is, right? Then for any x, its residual is orthogonal. So this is the residual direction, right? So we projected x onto this one dimension, and then we reverse the projection. This difference is orthogonal to U, right? Which means that you can show that by just taking the dot product of this vector with U, and you get, through manipulations, you get 0, right? So these two things are orthogonal, right? So then we take a look at this loss function that minimizes the residual, right? So this is the loss function we want. We want to find a U such that the residual of the reconstruction is minimized with the original training set. Using this property, we can show that if the U that maximizes this objective minimizes this objective. So it's just some straightforward manipulation of linear algebra. Right, so pictorially, what I just showed you is that we wanted to find a single direction of variation, such that if we project all the data along to that direction and we compute the residual, so this data set minus this data set, compute the norm, that is minimized. Right? So any questions on conceptually what's happening? Yes?
In this formulation where you multiply XX transpose and you're getting the symmetric form, if you just take the singular value decomposition of
You get the same answer.
You get the same answer.
Yeah, you get the same answer.
Okay.
Right. So here's a simple algorithm. In practice, you don't actually have to run these algorithms. You can just call a function in Python. You have your initial data matrix. You find the direction of you find this you loop through the dimension you loop through how many dimensions you want in order. You find the single direction of maximum variation, right? that captures the maximum variation, which is equivalent to minimizing the direction, the residual. We subtract that from the data, and then we repeat this process. You just greedy output. Okay, so if you call PCA in Python and on a data set or SVD, they give you the same U. The first k columns of U are guaranteed to be the k-dimensional subspace that captures the most variability of X, right? So if you want a k-dimensional projection of the data from some high-dimensional space down to k dimensions, or like 1,000,000 to 10, let's say, then the first k columns of U is guaranteed to be the k-dimensional subspace that preserves that captures most of the variability, that has the minimum, that minimizes the residual of the reconstruction. We just proved it for k equals 1 a few slides ago. The analysis is more complicated for high-dimensional k, but that's sort of the idea. Right. So you have this data, you call PCA, you get a U, and then I want to project it down to k dimensions that can summarize the data really well. I only want to look at k dimensions that summarize the data really well. And so I just take the first k columns of U, I apply, I project X onto this first k columns of U, I get a k-dimensional X prime, right? And that is my summarization of the data. Any questions on this before I go into a couple of examples? So if you've seen this before, this is probably all kind of boring. If you haven't seen this before, it's probably really confusing. There's a very sharp phase transition as you go from confused to bored. And hopefully it'll happen sometime as you're working on the homework. So let me go through some examples so you can see sort of how this works in action. Actually, I'll just do one example, but I'll go through it in a few iterations of it. So it's called eigenfaces. Here's a method. And it's basically they took a corpus of faces, right? Here I think it's just black and white, so it's grayscale. And they computed And here, for simplicity, every pixel is a feature dimension. These days we probably wouldn't do that, but just for simplicity, every pixel is a feature dimension, right? And so all the images are sort of the same size, and they ran. So each pixel is a feature dimension. They vectorized the image into a big vector. We've already seen this concept in the deep learning lectures, and then we run PCA on this data matrix of faces, right? And what we're visualizing here are the top 25 eigenvectors of U, right? So basically it says from the mean face, the direction of maximum variability is either to have hair that poofs out, right? And have more hair here, or to have less. So I think it essentially captures some correlations between male and female faces. Right? So if you go along the positive direct dimension here, you get male faces. If you go on the negative dimension, you get female faces, assuming that the hair is dark. Right. And then you can reconstruct, right? So here, you take the top K. You take the top K eigenfaces, you project X onto the top K eigenfaces, right? So the projection here means you take the original face, and then you do a pixel-wide inner product, right, with this eigenface vector, right? And you get a single number, right? And that number is one of these K numbers, right? So U transpose X gives you a vector of length K, and that each entry of that vector of length K is the inner product of the original face with this eigenface. Okay. So you get 25 numbers, and then you could reverse that projection by multiplying by U again, but rather than U transpose, and you get this reconstruction, right, in the original face space. So with a single face, with a single with few eigenvectors, you get a reconstruction that is not that good. With more eigenvectors, you get reconstructions that look closer and closer to the original face. Any questions on that? Okay, these faces are boring, right? Let's talk about some other faces. CS155 faces, right? So I took some photos of students who have taken the class this year and even years past, and I did the exact same thing, right? And so the first thing we need to do is we need to mean shift the faces, right? And so let's compute the average face. It looks roughly, roughly Asian and male in a vague way. I say that without commentary. And here are the top 12 eigenfaces. So this is a little bit hard to interpret because we're in RGB space rather than grayscale, but let's give it a shot, right? So if this is the mean face, right? And so recall that this image, this image you can go in both the positive or in the negative direction of this eigenface vector, right? And so if you go in the positive direction, I guess the skin complexion becomes lighter. And then if you go in the negative direction, I guess here there's darkness right here, so people with longer hair, it would sort of show that. It's kind of, we can all do this together, right? We can all try to interpret this together. So here, right? So people with, if you go in the negative direction, if you go in the I think it's the negative direction of this eigen. I could be wrong. It could be positive. Of this eigenface vector, right? People with a little bit bigger head, right? It differentiates people with a little bit bigger head versus people with a little bit smaller head, right? And so on and so forth. So here you see glasses are pretty distinct in this particular one, right? And of course, the photos are not all registered in the same distance, right? So some people are a little bit further from the camera, and so their faces are much smaller, and you can see that distinction in this eigenface, right? So these faces are much smaller. Okay, so let's look at some reconstructions, right, of actual CS155 students. So this is Michael. Here's Michael's reconstruction with 5 eigenfaces, all the way up to 150. Right? So in the beginning, Michael still looks a lot like the average face, using only 5 eigenfaces. So, I guess compared to the average face, the skin complexion is a bit lighter, right? And then you start able to see clear signs of wearing glasses by around 30 eigenfaces. And then the reconstruction, modulus and noise, is basically, you can tell that it's Michael after about 50-ish eigenfaces. Let's do another one. This is Ola. So in the beginning, she looks a lot like the average face. And then by around 30 to 50 eigenfaces, you can clearly tell that it's deviating from the mean face. Any questions on this? Yes?
How many faces are in this data set that you're using?
I don't remember. It's in the hundreds.
It's not that much more than 50.
It's maybe twice as much. Yeah, this is just for illustrative purposes. It's not the the most state-of-the-art application. It's just a little fun thing I like to do. Okay. So lots of people have mentioned the singular value decomposition, or the SVD, right? And so the SVD, for all intents and purposes, the SVD and the PCA, they give you the exact same information. SVD operates on X as opposed to XX transpose. That's the only difference. And so SVD gives you 2 orthogonal matrices because X is no longer symmetric, right? So the SVD gives you 2 orthogonal matrices, U and V, right? And if you sort of take this definition right, and you plug it into XX transpose, right, you get something that looks like this. You do some manipulation. This V is orthogonal, so you multiply it with its transpose. You get the identity. You get something that looks like this, right? So you get exactly the same PCA solution, and the lambda matrix is equal to sigma squared. So you get the exact same information back. V, by the way, right, corresponds to the new representation x prime. Right. So if you were projecting x, onto U, V is closely related to x prime, modulo multiplying by this diagonal matrix. So you can call SVD, you can call PCA. It doesn't really matter. Pick one in Python. Okay. So here's how we did the eigenfaces thing. We flatten each image into a vector, so these images are 250 by 300 by 3 channels. So the flattening gives you a 225,000 dimensional vector, right? And so, we have this data matrix of the number of pixels, including all 3 channels, by the number of people, entries in this data matrix, right? We mean shift it, right? So we compute the row-wise mean, right? And that's what this guy is if you were to visualize it, and we mean shift, so that, and this is a per column subtraction, and so we get this mean shifted data set. Okay. We compute the singular value decomposition. You could also do the principal component analysis. It doesn't really matter, right? And now we're only looking at the first k. We only care about the first k, so here I'm just throwing away anything but the first k columns of U. And so one thing is that the sort of thing that you have to be a little bit careful about is how to deal with this sigma, this diagonal matrix sigma, right? So what I did to create that data set that I just showed you is I simply put half of it multiplicative. I split it up multiplicatively, so you get the sigma square root and the sigma square root. I put 1/2 into V, 1/2 into U. And now every column of this new U is an eigenface, right? Right. So each of these that is one of the columns of this U prime matrix. And the coefficients, right? The coefficients of how this face projects onto these dimensions is stored in this V prime matrix. And that's literally what I did, other than cropping out all of your faces and saving them into individual into a file. Any questions? Yes.
Is there, I'm not sure if this is even a machine learning, but is there a way for it to train something to do that cropping automatically, to look at a face and make a square?
Yeah, probably. We're in academia, we're low budget. So we can, we can look at the coefficients, right? So, so for every eigenface here, I'm giving you the coefficients for Michael and Ola. So this is the first eigenface, and Michael is going in the negative direction of it, and Ola is going in the positive direction of it. Neither one projects strongly onto the second eigenface. Michael projects pretty strongly onto the third one. You can give your own interpretations about what's happening here. But it just goes to show you that now we can sort of summarize the characteristics of these faces using a small set of numbers rather than the original 225,000 pixel space. All right. So what are some limitations of eigenfaces? Well, you know, every dimension here is a pixel and color channel in the case of RGB pixels. And so, you know, it's not really very meaningful, right? And squared reconstruction in pixel space isn't always the best way of measuring how well you're actually, you know, modeling the data or capturing the data, right? You know, suppose each dimension had more meaning, right? If dimension 1 was the location of the left eye, right? Then the U components, right, would have a cleaner visualization, right? Like if there was a certain types of faces where the, you know, the eyes were further apart or closer together, the nose was wide, bigger or smaller, and that was correlated with, you know, the shape of the face, and the U's would capture those types of correlations as directions of variability, and would have a much cleaner interpretation. And in fact, people have done that. Here I just gave you a very, very simple example. People have done much more sophisticated versions of eigenfaces where the raw dimensions are not just pixels, but some semantically meaningful or feature representation. Okay, so just to summarize, right? We looked at two forms of unsupervised learning in this lecture, like clustering and SVD or PCA to reduce the dimensionality of the data representation, right? So for each data point, the goal is to, rather than store, you know, its entire feature vector, right, to store only k numbers that summarizes each data point. In the case of clustering, it's the cluster memberships or the cluster membership probabilities. In the case of dimensional reduction via PCA or SVD, it's the coefficients in some k-dimensional projection, right? One of the nice things about these forms of dimensional reduction is that they often have relatively easier, nice ways to visualize and interpret the summaries, right? You can look at representative images in the, or examples in the clusters, or you can actually try to visualize the direct dimensions, the directions of high variability in the projections, right, as we saw in the example on eigenfaces, right? This does depend on the semantics of the raw representation, right? Sometimes this is not so easy, but sometimes, you know, it can be fairly straightforward. So the next two lectures, we'll look at latent factor models, and which generalizes SVD into the cases where you have missing values, and you want to infer missing values. And then the lecture after that, we'll look at embeddings. And that's it for today.